Today we're going to talk about internal energy, okay? Internal energy is equal to the total energy of the particles. And you might be thinking, okay, I thought we talked about temperature, and temperature was about the energy of the particles as well. Temperature was the average kinetic energy of the particles. So say I have a small object, okay, and it's got a certain average kinetic energy. And then I've got a large object, and it has the same average kinetic energy. Well, the large object's going to have more energy overall, though, okay? So you can kind of think of it that way. These are two different things, okay? Temperature and internal energy are two different things. Temperature is a measure of the average, and internal energy is the total energy of all the particles all added up, okay? So the energy of particle 1 plus the energy of particle 2 plus the energy of particle 3 plus not however many particles you have inside your object that are moving around, okay? Internal energy is a scalar. It does not have a direction, okay? And temperature is related to the internal energy, okay? It's the total internal energy, but if you're talking about this object the entire time, well, it's got the same number of particles the entire time. So if its internal energy increases, it's not because it got more particles, it's because they sped up, okay? And if these particles speed up, then their average kinetic energy is going to increase, and therefore their temperature is going to increase. So they are directly related. If temperature increases, internal energy increases. If temperature decreases, internal energy decreases as well. The symbol for internal energy is the capital letter U. The units, it's an energy, okay? So we will be using joules. Now, they're not the only units that could be used, okay? Other energy units are calories or British thermal units, okay? But joules is what we will be using in this class. All right, so we're talking about energy again. So we're going to go back to conservation of energy and kind of look at this, all right? We said that the change in kinetic energy plus the change in both types of potential energy, remember there's gravitational and elastic were the two that we talked about, okay, that those two had to add up to 0, okay? If this one increased, this one needed to decrease, and vice versa, okay? But we said this was only true when there was no friction, okay? So this is if there is no friction. Now, we're going to say all energy is conserved, and we're going to include friction. So we're going to say the change in kinetic energy plus the change in potential energy plus the change in internal energy needs to add up to 0, okay? So let's say we have an object, okay, and it's falling off a cliff, all right? So it started off with a lot of potential energy up here, and as it falls, it's going to lose potential energy, and we're just going to make up some numbers and say that it loses 10 joules, okay, of potential energy. Okay, it goes down, okay? Well, what that means is that, so if these add up to 0, these two have to increase. Well, yeah, as it falls, it's going to speed up. It's going to get faster and faster. So maybe the kinetic energy up here was 0, and as it fell, it increased by 8 joules. Okay, well, these don't add up. Well, what else happened? Well, the thing we've been ignoring a lot of the times is air resistance, okay? Or if this was an object that was sliding along a surface, we've been ignoring friction, okay? Or saying that it's negligible. Now we're not going to say that, okay? Well, what happened to that 2 joules of energy? It went into internal energy, okay? And what types of internal energy did it go into? Well, it could have gone into, with friction, oftentimes there is heat, okay? So you've got friction, it speeds up the particles, and some of this goes into heat and it increases the temperature, okay? Another thing that could happen is it could go into sound, all right? When we talk or when there's sound, the air particles vibrate, okay? And their internal energy is increased as well, okay? So this is our new conservation of energy equation, and it includes internal energy.